Hello everybody, welcome to my How to Solve Systems of Equations mini lecture. Here is an example of a system of two equations in two variables, x plus y equals 3 and x minus y equals 1. It is possible to have even more equations, but usually one also has more variables then. Usually there are as many equations as variables. A solution of such a system of equations is any assignment of numbers to the variables which makes all equations true. For example, the system above has a solution x equals 2, y equals 1. Why? We plug it in, 2 plus 1 equals 3 and 2 minus 1 equals 1, so it checks. Checking whether numbers really form a solution is not hard, but we want to find solutions. This mini lecture shows how. Such systems of equations often result from word problems, like the following. Tom and Jerry are 6 years apart. Their age in years added is 38 years. How old are Tom and Jerry? We model this by assigning the variable x to Tom's age and the variable y to Jerry's. Assuming that Tom is the older one, the first sentence translates into x minus y equals 6. The second sentence translates into the equation x plus y equals 38. So we have two equations in two variables. A typical system of equations. How do we find a solution? Maybe you can guess one. But guessing is not always successful. There are many ways to solve such systems of equations, but I will only discuss the so-called substitution method here. By the way, some of you may claim that in our example above, adding the two equations is a fast method towards a solution, faster and easier than substitution method. But for many other examples, our substitution method is better. So here is the substitution method for two equations and two variables. Select any variable in any equation, say x in the first equation. Solve this equation for x. Call this the substitution equation. 2. In the second equation, substitute x by the corresponding expression from the substitution equation. Now you get only one equation in one variable, y. Number 3, solve this one equation for y. And number 4, get the solution value for x by plugging the solution value for y into the substitution equation. A frequent mistake is that students plug the substitution equation into the equation it came from. Don't do this. Plug it into the other equation. In our example, we pick x in the first equation and solve the equation for x to get x equals 6 plus y, step 1. Substituting x by 6 plus y in the second equation, we get 6 plus y equals 38, step 2. This linear equation in one variable y is easily solved. We get 2y equals 32 or y equals 16, step number 3. Plugging y equals 16 into the substitution equation x equals 6 plus y gives us x equals 6 plus 16, which is equal to 22. This example was easy. It was also linear. Both equations had the form number times x plus number times y equals number. Our next example shows that the substitution method can also be applied in nonlinear cases. An L-shaped pool, as shown here, should be created using two squares. The surface area of the pool should be 190 square meters and the length of the perimeter of the pool should equal 60 meters. What should the dimensions of the squares be? Let x and y be the basis of the squares, x being the larger one. The areas of the squares with bases x and y are x squared respectively y squared, so the area sentence translates very easily into x squared plus y squared equals 190. The second sentence translates into the equation x plus x plus x plus y plus y plus y plus x minus y equals 60, or 4x plus 2y equals 60. We solve the second equation for y. We subtract 4x on both sides of the equation and divide the equation by 2 to get y equals 30 minus 2x. Substituting y in the first equation by 30 minus 2x, we get x squared plus 30 minus 2x squared equals 190. We multiply the expression in the middle, foiling it or using a binomial formula, and we get x squared plus 900, the square of 30, minus 120x, which is 2 times 30 times negative 2x, plus 4x squared, which is the square of negative 2x, equals 190. Then we subtract 190 on both sides and collect the like terms x squared and 4x squared and get 5x squared minus 120x plus 710 equals 0. A quadratic equation which we can solve using quadratic formula, so we get x equals 120 plus minus square root of 120 squared minus 4 times 5 times 710, all divided by 2 times 5, and doing a little arithmetic, we get either 13.4 or 10.6. Then, since y equals 30 minus 2x, y is either 30 minus 2 times 13.4, which is 3.2, or 30 minus 2 times 10.6, which is about 8.8. The pool shapes for the two solutions are shown here. Both pool designs have the same area and the same perimeter. There is no reason to stop at two equations. If I could only convince you that three equations with three variables are not more difficult than two equations with two variables, just more tedious, of course. So here's our next example. A T-shaped pool, as shown here, should be created using three squares, the largest in the middle. The surface area of the pool should be 120 square meters. The length of the perimeter of the pool should equal 52 meters. Moreover, the length of the top of the T should be 16 meters. What should the dimensions of the squares be? Note that the surface area equals x squared plus y squared plus z squared if x and y and z are the dimensions of the three squares, and that the perimeter of the pool is x plus y plus y plus y plus x minus y plus x minus c plus c plus c plus c, which is equal to 4x plus 2y plus 2c. The length of the top of the T is x plus y plus c, so we have the following three equations. X plus y plus c equals 16, the top of the T equation. 4x plus 2y plus 2c equals 52, the perimeter equation. And x squared plus y squared plus z squared equals 120, the area equation. How do we solve impressive looking systems like this? We still use substitution method. The key is to reduce this three equation, three variable system into a two equation, two variable system, and then reduce this two equation, two variable system into a one equation, one variable system as before. So here's how to reduce a system of equations into a system of equations having one equation less and one variable less. Number one, select any variable in any equation, solve this equation for this variable. The result is called a substitution equation again. And 2, in all other equations, substitute this variable by the corresponding expression obtained in the first step. Then throw this equation away, the substitution equation, at least until later. We apply this step repeatedly until we arrive at one equation in one variable, which hopefully we can solve. Then we take all substitution equations we have thrown away in reverse order, and one by one we plug in the values of the variables we now know to get the value of the variable we eliminated at this step. Eventually, we should get values for all variables, a complete solution. In our example, we solve equation 1 for x, get our first substitution equation, x equals 16 minus y minus c, and substitute x in equations 2 and 3 by 16 minus y minus c. So we get 4 times 16 minus y minus c plus 2y plus 2c equals 52, and 16 minus y minus c squared plus y squared plus c squared equals 120. The first of the two remaining equations can be simplified to 12 equals 2y plus 2c and can be solved for y. We get the second substitution equation, y equals 6 minus c. Plugged into the other equation, we get 16 minus 6 plus c minus c, whole thing squared, plus 6 minus c squared plus c squared equals 120, or simplified 100 plus 36 minus 12c plus c squared plus t squared equals 120, or again combining like terms, 2c squared minus 12c plus 16 equals 0, or after division by 2, c squared minus 6c plus 8 equals 0. We use quadratic formula again. C equals 6 plus minus square root of 36 minus 32, all divided by 2, which is 6 plus minus 2 divided by 2, either 4 or 2. Next, we substitute these solutions for c into the second substitution equation, y equals 6 minus c, and get two solutions for y equals 2 and y equals 4. These two pairs of solutions we plug into the first substitution equation, x equals 16 minus y minus c, and get either x equals 16 minus 2 minus 4, which is equal to 10, or x equals 16 minus 4 minus 2, which is also equal to 10. There are two solutions, x equals 10, y equals 2, c equals 4, and also x equals 10, y equals 4, c equals 2. The first solution was already used for graphing this example here, and the second one is obtained by flipping this. So this is a general substitution method. It can be used to attack any system of equations with any number of equations and variables. I'm not promising success, however. If you have a system of linear equations, all equations you get will remain linear, but even then some complications can occur, leading to no solution or infinitely many solutions. If the equations in your systems are not linear, then the equations you get may become very complicated, and you may not even be able to solve some of them for a variable. So you may get stuck, but it's life. But for textbook examples, I think you should be relatively safe. Thanks for listening.